In this lecture, I'm going to introduce the concept of natural deduction, derivations, subderivations, and some rules of inference. Natural deduction is a way to test validity that is closer to natural human reasoning than truth tables, which are more like algorithmic computer reasoning. The truth table method is comprehensive, but it's also exhausting for humans and no fun at all. Humans do use valid arguments in quotidian reasoning, but by formalizing these valid arguments, we can free them from the vague and ambiguous nature of ordinary language and make them exact. Let's look at some ordinary examples of natural deduction. Suppose we go to the taco shop and I get burritos and you get tacos and we take them home. I eat a burrito, you eat a taco, and I put the leftovers in the fridge. The next day, you go to the fridge to grab your leftover tacos, and you see two bags sitting next to each other. You grab one bag and look inside. It's not a taco, it's a burrito. So you put it back, grab the other bag, and put it in the microwave without looking inside. How did you know it was a taco in the bag? It wasn't by the use of some mystical intuition or the rigorous construction and analysis of a truth table. It was by natural deduction. The metaphor I like to use when teaching students basic logic is the mechanism behind the face of a clock. Just like you can plainly understand that the second bag contained a taco, you can plainly see the time on the face of a clock without troubling yourself with every movement of every gear, cog, or spring behind the time being displayed. But you know they're there. Logic gives us a look at the machinery working in the background of our reasoning. Another good metaphor that students find useful comes from John Locke, who said, "Logic is the anatomy of thought." Just like in my metaphor, Locke is recognizing that even though we can't see the organs, muscles, and bones underneath, we know that they are there. We don't list every muscle flexion in the body when we explain a person's forward ambulation. We can just say that they're walking forward. So, let's make the leftover Mexican food example perfectly clear. You know that P or Q, either the taco is in bag 1 or the taco is in bag 2. Not P, it was not in bag 1. Therefore Q, the taco is in bag 2. This is how natural deduction works, and it reflects our natural form of reasoning much closer than truth tables do. Of course, we can always make a truth table to prove an argument's validity, but once we get into more interesting arguments with more than 2 premises or 3 premises, we may want to use this more natural method for the sake of our sanity. This particular argument form is traditionally called a disjunctive syllogism, and it's a kind of disjunctive elimination, which is what Teller calls it. Let's use this same example to explain another valid form of argumentation, traditionally called modus ponens. Let's say that you open the fridge and reach in for the first bag, and you think explicitly to yourself, if the burrito's in this bag, then the taco is in the second bag. You look inside, and there's a burrito, so again, you grab the other bag and throw it in the microwave without looking inside. This is another example of natural deduction. Symbolically, it would be if P, then Q, or if the burrito is in the first bag, then the taco is in the second bag. P, the burrito is in the first bag, therefore Q, the taco is in the second bag. And this is what Teller calls a conditional elimination. Let's work our way up to another valid form of argument, traditionally called the pure hypothetical syllogism. Suppose some kids want to play soccer, but it might have rained last night, and they argue, if P, then Q. If it rained last night, then the grass is wet. If Q, then R. If the grass is wet, then we can't play soccer. By looking at this, it seems obvious that we could conclude, if P, then R. If it rained last night, then we can't play soccer. But we still need to justify it. We can think hypothetically and assume P. Then we can eliminate the first conditional using modus ponens, giving us Q. The grass is wet. And we can do the same thing with the second conditional, which gives us R. We can't play soccer. So, What this finally amounts to is if P is true, which we assumed, then R is true, giving us the final conclusion, if P, then R. In this process, we've also proven that we can use the hypothetical syllogism as an inference rule. So, anytime we see premises in the form if P then Q, if Q then R, we can conclude if P then R. Another inference rule introduced in this chapter is the disjunction introduction, also known as addition, which states that we can infer P or Q from the mere truth of P, because after all, only one disjunct needs to be true for the overall disjunction to be true. Let's work through this one without giving any ordinary language translation. The goal of this argument is to prove that C or D is a valid inference. Our initial premises are 1. If A, then not B, 2. B or C, and 3. A. So, you can see the first move available to us if you look at lines 1 and 3. Using modus ponens on lines 1 and 3 gives us not B on line 4. With not B on line 4, we can now use it in a disjunction elimination, citing lines 2 and 4 to give us C on line 5. From there, all we need to do is a disjunction introduction, and we can conclude on line 6 C or D, proving that C or D is a valid inference in this argument. In this section, Teller diagrams all of the inference rules introduced so far, but I'll include a few more. Since the replacement rules were explained in Chapter 3, when we discussed logical equivalence, I'll only explain the inference rules that Teller hasn't covered. The first is another type of hypothetical syllogism, with a close family resemblance to modus ponens. Modus tollens, also known as denying the consequent, warrants some explaining. Recall one of our previous examples, here in the form of modus ponens. 1. If it rained last night, then the grass is wet. 2. It did rain last night. 3. Therefore, the grass is wet. Let's say it didn't rain last night. It seems like we could say 1. If it rained last night, then the grass is wet. 2. It didn't rain last night. Therefore 3. The grass is not wet. However, if we check the truth table, we'll see that this is not a valid inference. After all, the grass could be wet for some other reason, like the sprinklers came on or something like that. It just does not follow that if it didn't rain last night, then the grass won't be wet. However, if the grass is not wet, then it couldn't have rained last night. So, that would look like this. 1. If it rained last night, then the grass is wet. 2. The grass is not wet. Therefore, in line 3, it didn't rain last night. If you check this version of the argument, you'll find that it is valid. Finally, we have the dilemma, also called the constructive dilemma. It has a disjunction, 2 conditionals as premises, and each disjunct is an antecedent in one of the conditionals. The conclusion will also be a disjunction of the consequence of the 2 conditional premises. Consider this argument. Either a Democrat or a Republican will win the election. If a Democrat wins, then taxes will go up. If a Republican wins, then healthcare will become more expensive. Therefore, either taxes will go up or healthcare will become more expensive. We'll see reasoning like this become more common as elections approach. So, let's symbolize it. Either P, a Democrat, or Q, a Republican, will win the election. If P, a Democrat, wins, then R, taxes will go up. If Q, a Republican, wins, then S, healthcare will become more expensive. Therefore, either R, taxes will go up, or S, healthcare will become more expensive. As you can see, an argument with this many premises is very tedious when checked with the truth table. So, let's take a look at another simple argument. In this argument, we're trying to prove that not D or E is a valid inference. Our initial premises are 1. If not C, then not D. 2. Not C. By citing lines 1 and 2 and applying modus ponens, then we can derive not D. Now that we have not D isolated, we can cite line 3 and use a disjunction introduction to give us the conclusion we want, not D or E, showing that it's a valid inference. As a final example, I'll use one of Teller's longer exercises. The aim of this example is to show that if F or not D, then B or not P is a valid inference from this argument. To show that this is a valid inference, we're going to use Teller's strategy of making an assumption. And what we're going to assume is the antecedent of the conditional conclusion that we want to prove. So the first thing to do is to assume the antecedent on line 5 outside of the scope of the original argument. Then we'll reiterate premise 3 on line 6 and use lines 5 and 6 to do modus ponens. On line 8, we'll reiterate premise 1 and also reiterate on line 9 premise 4. Using 8 and 9, we can do another modus ponens, giving us K or not F on line 10. Then we can use lines 7 and 10 to conduct a disjunction elimination, giving us not F. And then we can conduct another disjunction elimination using lines 5 and 11. Using not D from line 12, we can conduct a disjunction introduction, giving us not D or K, and then reiterate premise 2 on line 14, so that we can use lines 13 and 14 to conduct another modus ponens. This gives us B on line 15, which gives us what we need to build the consequent of our target conditional statement using disjunction introduction. Since we assumed the antecedent on line 5, we can now say, if F or not D is true, then, like it says on line 16, B or not P is true. So, we can discharge this assumption and demonstrate that this is a valid inference. Next time, we're going to finish off this basic logic course with Chapter 6 from Teller's Logic Primer. As always, practice by trying a few of Teller's exercise sets on your own. And if you need any help, don't hesitate to ask.